session. The first talk is going to be by Clément. Some of you might know him as Clement. And he's going to tell us about how to deserialize network protocols in COC with minimal effort and maximal correctness.
Hello, everyone. Thanks for attending my presentation on deriving correct by construction decoders and encoders from binary formats. We all know that encoding and decoding bugs are everywhere and particularly painful to deal with. We've seen the long stream of name vulnerabilities, of vulnerability reports, and one particularly vulnerable place where these bugs are damaging is network code. The reason is that network code spends a significant fraction of its time doing encoding and decoding of binary formats. In addition, the inputs to network programs are typically entirely controlled by the attacker. And finally, mitigations that you would typically see, such as adding assertions to your code or adding bound checks or other mitigation strategies, will usually turn a bug in which an attacker gains control of your system into a bug where the attacker crashes your system, hence leading to a denial of service issue. You would think that this might be a solved problem by this point. We have great stories about serializing and deserializing, for example, for context-free grammars. But there's a reason why it's so tricky for binary formats. The reasons are twice, actually. There's two reasons, actually. One of them is very frequently those formats are context sensitive. For example, you will write a list, and then you'll prefix that list with its length. Or you will have a checksum that needs to sum the bits of all the encoded packet to be written out to the end of the packet. And very often, those formats are underspecified. It might be the case that some fields can be left at any value, which means that it's particularly hard to specify what it means for an encoder and a decoder to be correct, because the decoder needs to handle all the values that a valid encoder might produce. So it needs to support compression or no compression and similar issues. So here's how we approach the problem. We built this framework called Narcissus. It's in the style of combinators. The key idea is that you'll write one single format specification. This format specification will be non-deterministic, meaning that it will describe the whole universe of possible encoders. And then from this, we'll generate one encoder and one decoder, as well as a proof for both of these that they obey the format. Let me start with a very concrete example. On the screen at the moment, you have a definition of a record. It contains two fields, the ID of, say, a weather station or a measurement station on 8 bits, and then a data piece that is 16 bits of something that this station measured. We will describe how to encode this thing. This is the description of a format. It's not deterministic because, as you see in the middle of the format, there's an unused word. This means that the encoder can put anything in there. And we'll also encode the data and the station ID. And then we have this magic incantation at the bottom. All of this is in the context of the COC proof assistant, which will generate the code that is now going to be printed on the right. On the right, you see the encoder that was generated. It starts by, so it's in a monad of encoders. It can just write to an output buffer. It starts by writing the station ID, then writes just zeros because there were no constraints on that field, so why not put it to 0? And then writes the data, first splitting into the low 8 bits and the high 8 bits, and then writing those two. The decoder does something similar, except you'll notice that it actually does not care what value was written to the unused field. But besides that, it just gets all the data from the byte stream that it got as input, and then returns a record of the right type. Now let's make one modification. I'll add a constant, let's say it's a version number, to that format. So the underlying part shows what changed, and I'll rerun my magic tactic. At this point, the encoder is fairly simple. It just writes that constant. But the decoder has to check that the proper constant was written. So unlike the unused word case, the decoder has extra work to do to verify that we're decoding a packet that contains the correct constant, correct version number in this case. Let's make another modification. Instead of a single data point, I will have a list of data points. So I change my record definition as well as my format. And now I say I need to write each of these data points to the packet. If I try to generate this with the magic incantation I mentioned before, things will fail. The reason why things will fail is that there is nowhere in the packet written the length of the data, which means that I cannot determine how long this data should be. For example, in this packet, there could be a second list of data passed in this format, and then I wouldn't know where the first list ends and where the second list begins. So I really need somewhere in the packet to encode that length. So I'll replace my unused word by the length of my data written on 8 bits. However, this will still fail. This time, it tells me that from no particular assumption, I should be able to prove that the length of the data is less than 2 to the power 8. And this is because if I try to write a number that's too large in an 8-bit field, then the length will be truncated, and thus I will not be able to recover the full packet when I decode. As a result, I need to add an invariant that says that the only valid source values are those that have less than 256 values in their input. So I add this invariant that I showed on the board. And now synthesis can proceed, and I can generate an encoder and a decoder. So the encoder writes the length and then write each of the words that were in the data. And the decoder reads the length and decodes everything that it found in the packet. There's been a lot of work on this, and you might be wondering, how is this not the same as one of the many things I listed on this slide? The key features we have are that we claim the specs are fairly readable, and we hope that you'll agree with us after seeing what you just saw. We have proofs. The formats are extensible through tactics, and I'll show exactly how this works later. We handle context sensitivity, so the length of a list and the list can be written at totally different places in the packet, and we'll still handle this properly. And we handle the fact that sometimes you have multiple choices in encoding. Let's get a bit more formal. We define a format as being a set of source and destination values, and we define a families of format combinators that allow you to combine those formats, like the append combinator that I showed earlier with a double plus, or a union combinator that allows either formats to be chosen. An encoder takes a source value and returns an option in the target type, and its correctness is characterized by the fact that if encoding succeeds, then the pair of the source and the target value should be allowed by the format, and if encoding fails, then there should be no target values in the target type that correspond to the source according to the format. A decoder goes from the target type into the source type, and here the theorem is a bit different. For any source and target values are allowed by the format, decoding the target should yield the source. The reason why there's a difference between the encoder and the decoder is that when you generate one encoder, it should be one of the many encoders allowed by the format. But when you generate a decoder, it should accept to decode any values that might have been produced by the format. This definition of decoders, forces you to recover the whole source. It does not allow to decode just part of the packet. The paper defines a more complex concept of views that allows you to talk about the correctness of a decoder that just recovers some of the information in the packet. We have round-tripping properties. They essentially tell you that encode and decode kind of work together, but really these are not enough. So the first one says if you manage to encode, then decode should give the same value. But the second one just says if you manage to decode and then you encode back to something, then it should encode back to something, but it might not be the same value. For example, if you decoded a compressed packet, your encoder might never actually compress, and so you might get a decompressed packet as the result of re-encoding. So we have automatic support for deriving implementations, and I'll show how this works. We start with this relational language of relational formats. Our output type is a list of bits. However, there's an optimization that I won't talk too much about here that actually then translates the programs into programs that process lists of bytes. And the target language is just Galena, the language inside of the cockproof assistant, augmented with the error monad. The key insight is that when you look at the proof of a combinator, really what it tells you is if you want to prove that a particular, say here I'm talking about encoders, if you want to prove that a particular encoder verifies a specification, then it's enough to prove that those two sub-encoders, there's a number of sub-encoders, actually work. So we take these rules, these correctness rules, and then we apply them repeatedly, and progressively we'll build our encoder or decoder. And this strategy is complete for the base types that we support in the framework, and if you extend it, then you have to provide the corresponding lemmas. So let's see a very concrete example. You'll remember this format that we saw before. It has a word, then the length of the data, and then the list of data. And what we'll do is we'll accumulate information that we've gleaned as we decoded the packet, or we constructed the decoder, and we'll use this information to recover the packet at the end. So at first, our decoder is nothing, essentially. We have our format, and then we have this initial constraint that was the invariant we introduced earlier. The first thing we'll do is we'll match the syntax. It says format word. So we'll do get current byte, which just reads 1 byte out of the output. And we'll learn one thing, which is that the station ID here should be the word that we just read. We'll repeat the process. We see a NAT being written out to the packet, and we see that it's the length that we're writing out. So we'll add 1 get current byte, and we'll learn another fact that says that the length of the data should be this ln that we just read. Now we see a format list. So here we'll use the list decoder. And I omitted what we pass as the body of the list decoding function. But we gleaned an extra bit of information that says that the data should be this L. And finally, with all the constraints that we've accumulated, we can actually reconstruct the source value in the source type sensor message. from this W and this L that we got. So how do you evaluate this work? So what we did is we took a collection of encoders and decoders that are commonly used. We did Ethernet, ARP, IPv4, TCP, UDP, and a few others actually. And then we integrated into this really cool project, which is called Mirage OS. It's a unikernel. That means that you write an OCaml program, and it'll give you a minimal set of libraries. They like to call themselves library operating systems. So they'll give you a minimal set of libraries that you'll link with your code, and you can run directly on a hypervisor. Of course, they do networking, so of course they have a set of encoders and decoders. And the encoders and decoders they have are written in OCaml. So it was a fairly natural target, since Coq has the ability to extract OCaml code from Galena programs. The aim of this evaluation was to see how easy it was to actually write formats and see how much we lost in terms of performance. One of the reasons to actually lose performance rather than gain some is that we tried to make the integration as non-invasive as possible, which means that we put all the decoding in one place inside of Mirage OS, and we didn't go modify the rest of the program. And in some places, Mirage OS will actually delay some checks. So for example, a checksum will be computed much later after decoding. And so with our integration, it ends up computing checksums twice. So here's how you proceed. You read the RFC. It looks roughly like that, plus a bunch of text. Then you write the encoder specification. So here it's for UDP. You write the source port of your packet, then the destination port of your packet, then you write the length of your payload, then you write a checksum with a custom combinator that we had to write for this particular example, and then you actually write the payload of your packet. The typical effort it takes to add a new combinator, to add a new format like UDP, I'd say it's about 10 to 20 lines of format specification. That's what we were looking at, plus 10 to 20 lines of record declarations, like we saw before. And once you have this, you can actually run the derivation tactics. So you get an encoder for UDP, which looks fairly similar to the examples we've saw before, and a decoder for UDP that also looks fairly similar. So the experiment was to replace Mirage OS's TCP IP stack with our own encoders and decoders. We extracted to OCaml, added a few custom data structure like a proper byte string to make things fairly efficient. And then we ran the Mirage www website, which is the website of the Mirage project, using their code, and tried to measure how much slower this made loading the main page of the website, the blog page of the website, from the perspective of a client. And so we added one by one different parts of the stack. So first we replaced their Ethernet encoding and decoding primitives by ours, and then IPv4, and then TCP. And overall, the overhead, the change in loading time is about 10%, or a bit below 10%. There's a lot of extra material that is covered in the paper. When I gave the definitions of encoders and decoders, I lied. These encoders and decoders actually manipulate state. And this is particularly useful when you have state compression, because you need to maintain data structures as you go through encoding and decoding to be able to produce the encoded or decoded packet. I also didn't talk about the byte alignment phase. The idea here is that it's easy to specify encoders and decoders by talking about lists of booleans, so the individual bits in the packet. But for performance, you actually want to pack them 8 by 8 and deal with bytes. So we have a second phase of compilation that actually translates from bit encoding to byte encoding. We give concrete examples of how it feels to extend the system. So the idea is that you'll have to write a correctness theorem for the encoder, a correctness theorem for the decoder, as well as a tactic that decides when to apply it, and of course the actual specification of the format. And we give the concrete example of doing this for checksums in the paper. And of course there's a lot more experimental data as well as details on the related work. There are a few next steps that we'd like to take. One of them is that currently what we do is we decode the entire packet into a structure, and then further code can use that structure. But it would be much nicer to actually take the code that's going to use the structure along with the decoder, fuse these two parts, and then force the decoder to just generate the data it needs and no more than that. We'd also like to start targeting larger formats that could be various multimedia formats or archives. There's a wealth of bugs in that domain too. And finally, we'd like to try to do certified extraction. So currently what we do is we extract to OCaml, but that means that we have a dependency on the correctness of the extraction in Coq as well as that of the OCaml compiler. And also it means that it's particularly tricky to integrate with code that is not written in OCaml, such as C. I think that concludes my talk. Narcissus is available on GitHub, and it should be easy to use, so please give it a look. Thank you.
So you gave us...
could you wait for the mic?
So you gave us benchmark results from a system test, loading the entire blog page. Did you also do micro benchmarks where you benchmarked individual encoder-decoder pairs against the OCaml implementation?
So we did do micro benchmarks. The paper has actually 2 sections in the evaluation, and the first one is about benchmark individual packets. This just gives you absolute numbers. It does not compare against Mirage OS's encoders and decoders. The reason for this is that Mirage doesn't clearly separate what is encoding and decoding for the rest of the code. So it instead reads a bit of the packet, and then further along it decodes, it verifies the checksum. It's hard to isolate exactly that part.
So let's take a question from Slido. Why can encoders fail?
Because the data that you feed into the encoder might not verify the predicate, the invariant that you put on it. So for example, if you ask the system to encode, as in the original example, a list that has more than 256 elements, the encoder should fail. Also, there's another reason why they should fail. You actually pass to the function a buffer that should write into. If it happens that the buffer you passed it is too small, then the encoder will return an error code to tell you that it could not fit the packet into the buffer.
Hello. I was wondering if your language supports data formats where one field is computed from another field. So you showed an example of where you stored the length of the list, but what if I store 2 times the length of the list? Do you need to worry about inverting functions and things like that then?
So we do support this, and one example where this pops up is, I think UDP. The length that you write is actually the length of the whole packet, but what you really care about is the length of the payload. So the length that you write is the length of the payload plus the constant size of the header. You do have to worry about invertibility. In fact, it's just when you prove the 2 theorems about this particular encoding style that this pops up.
Another question from Slido. Did you find any bugs in existing RFCs or in what Mirage OS did before?
Certainly not in RFCs. In Mirage, no, because they fixed the bug that we end up running into. So yes, but then when I get pulled before I reported the bug, it turned out that it was already fixed.
In your example, I didn't understand how the length combinator works. So what does it do?
The length combinator. There's not really a specific combinator for length. Instead, you detect that you're writing a list. So let's see from the decoder's perspective. I think it will help to think of it that way. When you decode a list, the list decoder will add as a prerequisite, as a premise, that from the context of accumulated information you have about the packet, you can derive the length. If you do not have this, that is, if you have not already previously from anywhere in the packet decoded something that gave you the length of the list, then you will not be able to satisfy the premise of the list decoder.
But in the format when you write length, is it the usual coq length?
Yeah, it's the list of length from coq.
Okay.
Correct.
Question from Slido. Using a website as a benchmark incurs significant overhead on top of what just the network stuff. So do you have benchmark results that are just more strongly focused on network itself, like iPerf?
We didn't run the iPerf benchmark. We have micro benchmarks in the paper that are specific to individual formats.
No.
Hi. How hard it would be compared to your approach to implement something like of formal verification plugin to protobuf or message pack or something, because those formats are widely used, and maybe it would be more practical to formally verify that their users are doing something right.
Sorry, can you actually repeat the question, please?
Sorry. How hard would it be to implement a formal verification plugin for protobuf or message pack or something like that instead of what you did, instead of new format language?
I think those approaches are they complement each other nicely. In fact, one of the authors of this paper, Ben, also has a paper on verifying protobuf encoding and decoding. The problem with so this fits in this. You could fit this in this framework. They use the same definitions, but not the actual framework to do this. The problem with focusing just on protobuf or say ASN.1 or those extensible styles is that it does not let you handle. There are many already existing network formats that are not instances of protobuf or ASN.1.
think I have to cut it here to give enough time for the next speakers. So
Thank you, everyone.
thanks, Clement, again.